So myself, over to Banerjee. I'm representing ACS research here for the paper Radiant Phase Profile Reflecting Surface Design for Sectoral Sensing Application. Now, if I go straight to the design challenges that we face today for 5G or 6G systems, the problem comes inherently with the high frequency is the path loss associated with it. As high as we climb in the frequency range, say at 26 gigahertz or 60 gigahertz, the free space path loss becomes a major problem that has to be mitigated. Now, what can be the solution for it? To design systems or radiators which are highly directive in nature. That is, we narrow down the beam width and we control the beam in real time so that the path loss is minimized and we only address the users required at that point of time. That is real-time beam steering and beam control. How do we achieve that? Here I have just represented the free space path loss equation for high frequency. You can see it is directly proportional to the frequency of operation. So as I have said, that gradually we will need real-time beam steering and beam control for high frequency 5G applications. Like if I take a use case of this auditorium only, we can see on the right hand side the auditorium is more densely populated. On the left hand side of mine, it is sparsely populated. So if we can effectively direct the beam towards the region where the users are located, then we can have a energy management in terms of power. Now, one solution comes in the form of reconfigurable intelligent surfaces. Now, here I'm showing a few use cases. You can see that if we have an obstacle or if we have some legitimate users and some eavesdroppers, then using the reflecting surface, we can reflect or redirect the beam to the specified user required for the purpose or required at the time of operation. Now, how do we intend to achieve that? Below on the right hand side, I have shown a reflecting surface on top of which I am writing index 1, index 2, and index n. That is a phase profile or phase control reflecting surface that is dependent on the source radiation which is falling on the surface at a specific region. Depending on the phase of that region, the beam will be reflected to a particular user. That is the advantage of using a radiant phase profile surface. Now, how do we achieve radiant phase profiling? For that, we have two options. We definitely for meta surfaces or meta materials, we start with unit cell design. Now, what are the unit cells in terms of meta materials? The unit cells can be either reflective or transmissive, or in some cases, depending on the application, absorptive in nature. In this article, we are considering the reflecting type. Now, what is the speciality of a metamaterial-based reflecting unit cell? That is, it will reflect the incoming signal, but the phase of the reflected signal can be controlled in real time depending on the unit cell design. There can be two ways to control the phase. Either we incorporate a lump element on the metasurface unit cell, such that like some variable diodes or twin diodes, or we can use the geometric properties only, the geometric shape only, to modulate the phase of the reflected wave or the transmitted wave. In this case, we have a reflecting unit cell with a Minkowski shaped patch on top of a dielectric substrate backed by a metallic round plane. Here you can see, as the Minkowski shape is determined by the dimension A, as the dimension A changes, for all the values of A, S11 value is nearly at 0 dB, at 26.5 kHz, which is the frequency of operation. But at that frequency only, for different values of A, we are getting different reflection phases. Now, for those different unit cell shapes, I am naming them as cells A, B, C, D, or E. Now, how they can be used? I can profile the metasurface. Now, the 2D larger metasurface in two ways. Here I'm doing it in two ways. One is the on-centric way, and the other is the symmetric way I'm on it. In the on-centric way, we are taking, if I consider the dimensions, A is the minimum reflection phase at minus 100 degree, and each type of cells that gives us the maximum reflection phase at plus 50 degree. So the on-centric one is the one where we start with the minimum reflection phase at the center, and gradually as we move gradually outwards, we are having a higher range of reflection phase. For the symmetric case, we are only maintaining a row-wise variation which is repeated over the two-dimensional surface. Now, how this is studied? Now, for the RIS structures for practical operations, not only the surface but also the positioning of the source radiator is a point of importance. Here we have tried to characterize the reflecting surfaces based on the placement of the primary radiators also. You can see. Okay. So I'm defining the angle of incidence. The Hall antenna is placed in front of the radiating surface at an angle, and we must mention that the angle of incidence is not equal to the angle of reflection. The horizontal distance of the Hall antenna radiation pattern is kept fixed. The vertical distance is maintained during the simulation such that the radiation always falls at the central position of the metasurface. Now, we know that the Hall antenna is such a conical radiation pattern. But in using the reflecting surfaces, we can reflect the radiation pattern from a conical beam to a sectoral fan beam type of pattern, which is characterized by two parameters. I'm saying the elevation angle and the azimuthal spread angle. That is, towards the desired direction of reflection, I'm measuring the angle of reflection. And as the conical beam is spreading out to a fan beam to a sectoral pattern, that sectoral pattern is characterized by the azimuthal beam width, which are shown below. Now, as I have mentioned, that depending on the primary source radiator placement also, we can observe sectoral operation of the reflecting surfaces. Here on the left-hand side, I have shown if the metasurface is divided up into 4 quadrants, and we can ensure that the radiator is placed at specific quadrants to illuminate the specific regions of the metasurfaces. Then we can have on the right-hand side, as we can see, sectoral reflection performance of that fan beam. That is, over the 360 degree, we can rotate the fan beam according to the placement of the radiator or the placement of the metasurface, ensuring that the primary radiator is illuminating one particular quadrant of the metasurface. Now, the last thing we can ask that why we are going for on-centric and symmetric arrangements. We could have gone for one particular arrangement only. Why I am presenting two different arrangements? Now, here we can see, as we have said, that depending on the primary source radiator placement, the reflection performance will be varied. So, for practical use cases, the angle of arrival or angle of incidence may also vary, and the tolerance has to be studied that as we vary the angle of incidence, how the angle of reflection is changing. Here we can see for the on-centric and the symmetric cases. For the on-centric case, as the angle of incidence is increasing, the angle of reflection also increases. But for the symmetric case, as the angle of incidence increases, the angle of reflection gradually decreases. So these two arrangements is just two distinct reflection performances from the RIS point of view. Now, these are more or less the simulation work we have done. The fabrication and the practical validation of these surfaces are in order. The achievements are that this present two novel and independent radiant phase profiles, reflecting surfaces, which demonstrate distinct reflection performances, and depending on the source radiator placement, we can have a 360 degree maneuverable operation. And furthermore, these designs are entirely passive in nature. So for further control, we can incorporate directed diodes or other lump electronic components to ensure real-time beam control and real-time phase profile control as well. That can be the next step of our this work. So these are some of the cited references. Thank you.